Then it wants to find the tension in each cable, TBD, TCD, and the reactions at that ball and socket at A, which we have to determine what the proper types of reactions are going to be. And we're given really the only thing relevant here is going to be the diagram that we're provided with. So what we need to do is make the free body diagram that we're going to use to create our equations that we're then going to solve to get what we were asked to find. So what's the object that you chose to isolate from its supports, from its connections for this one? The blue platform is a good choice here, so we will disconnect it from the ball and socket connection, which means we'll be able to then see the reactions at A, whatever they may be. We're going to disconnect it from the ropes it's attached to at B and C, which means that we'll be able to see the tensions in those ropes as they're going to be affecting that blue platform that we kept. Keeping their given coordinate system. Okay, so there is the platform. We have one applied force acting on it, that 300 Newton force. Acting at, they actually don't give that a name. In my notes, I just called it E. Right, that's the only applied force here, so now we need to include things that come from supports and connections that we've disconnected it from. So what's other forces, other couples that are going to be acting on the blue platform now that we've disconnected it? Right, the tensions from the two ropes that we disconnected at C and at B. We know that the tension in the rope will act along the length of the rope. Now these are two different ropes, so they potentially could have two different tensions because they each individually go and meet at D, but are tied together separately. D is not a pulley, which would mean it's one continuous rope. So one tension goes from B towards D. That's my TBD. And another tension goes from C to D, I'll call TCD. Right, so those are the tensions. What else is going to be affecting my platform? What other forces or moments does the platform undergo? Right, we've disconnected it out of that ball and socket joint, so we need to include what the ball and socket joint did to the platform. So we want to think, what are the translations it prevented? What are the rotations it prevented? So thinking about, yeah. Right, so the ball and socket prevents all translation. We can't pull it in or out of the X direction. We can't move it in the Y direction or in the Z direction. So all spatial translations are prevented because the ball and socket is there. So it's going to be three components of force. Yeah. So at A, because all the translation is prevented, I'll have a component of force in the X. I'll assume is positive and call it AX. In the Z, I'll call it AZ. And along the Y, and call it AY. I'll reiterate for any of the support reactions that it can't move in or out in the X or the Y or the Z. Just for simplicity and for convenience and for consistency, I assume they act in the positive direction, and I could turn out to be wrong later. If it were, again, a normal force where it can only be pushing, or like this tension, I know the tension can only pull. Those directions I am certain of. Now, as far as rotations go at A, or what, if any, rotations are prevented because of that ball and socket connection at A. We can rotate around Y at A at least a little bit. Eventually it's going to prevent us, but we can rotate it somewhat around the Y-axis. And around the Z-axis, again, we can rotate it that way too. So all rotation is allowed at least a little bit at A. So because all rotation is allowed, then there's not going to be any couples acting at A. So we only have those three forces, no couples at A. The last thing we need then on our free body diagram are coordinates. They'll make the writing of equations easier. Based on where our coordinate system has its origin, we'll have A at negative 0.500. All of these will be in meters. D we need because that's where the ropes terminate at 0, 0, 3. C is going to be located at 1, 1.5, 0. And B at 1, negative 1.5, 0. And this point E that I added will be at 0.5, 0, 0. I have my coordinate system marked out, x, y, z. All my points are labeled, so that's my dimension step. I have the forces from the supports, and those were applied, labeled with unknowns, or like the 300 I knew. So this is my complete free body diagram for this object, the blue platform. All right, let's start with the force equations. These are going to be more straightforward. Looking at our x direction, we have all of ax I assumed was positive. I'll have a component of the tension BD, so negative 2/7 TBD, and minus 2/7 TCD. I have AY in the Y, 3/7 TBD minus 3/7 TCD. And in the Z, AZ, I have my applied 300 Newton force in the negative Z direction, plus 6/7 TBD, plus 6/7 TCD. In these three equations, I have all 5 of my unknowns present, so I can't easily use these yet in order to solve for any of the unknowns. So the force equations are done, but at least immediately, they're not too useful yet. Now the harder part, taking my moments around, I think A is going to be the easiest point here. Again, by choosing A as the place to take the moment about, these 3 AY, AX, AZs are not going to appear since their position vector is 0 from point A. So it eliminates 3 of my unknowns immediately, which means that these will generate equations that will give me numerical answers much more easily, since I'll get up to 3 equations out of them. So if I take the moment around A, I still do have 3 forces that contribute to the moment around A. I'll go right to making their determinants here. I'll have a moment caused by the 300 Newton force in the negative Z direction. And I have to use RAE to find that's the proper position vector to use. So point E minus point A will give me 1 in the I, 0J, 0K. I add to that the cross product from the vector. I'll do TBD next. So I have to use RAB cross TBD. The position vector, the coordinate of B minus the coordinate of A, is going to be 1.5, negative 1.5, 0. Here, because I don't know numerically what TBD is next, I have to put its components in with that unknown magnitude. So I put in negative 2/7 TBD, 3/7 TBD, and 6/7 TBD. So I do have an unknown TBD value, but I have to multiply it by the I, the J, and the K component of its unit vector. And I do the same thing for the moments caused by TCD. I have to use RAC, which will be 1.5, 1.5, 0. And then the components of TCD, which will be negative 2/7 TCD, negative 3/7 TCD, and 6/7 TCD. There are no couples in here that I need to include. The only moments are caused by this force, and this force. So 3 cross products I need to take to get the total moment around point A in its vector form. Questions on setting up the three cross products I need to take. So again, RAE cross that 300 Newton force, RAB cross TBD, and RAC cross TCD, everything in its component form. I expand out these cross products, and I can group everything in front of I, in front of J, and in front of K together. In front of the I terms, bringing this back up to here. For the I terms, I'll get 1.29 TCD minus 1.29 TBC. My J coefficients, I get 300 minus 1.29 TCD minus 1.29 TBC. And my K, I will get 0.214 TBD minus 0.214 TCD. Okay. Again, when I expand out all those cross products, that's all the I terms, the J terms, and the K terms put together. If I split these out, if I make equation 4, 0 is 1.29. I'll simplify this a little bit. TCD minus TBC. If I bring out my equation 5, that's 0 is equal to 300 minus 1.29 TCD plus TBC. And my equation 6, I'll get 0 equals, I can pull out the, this is actually a negative here. Pull out that negative 0.214 TCD plus TBD. Oh, that is not negative actually. Right, separating them out, so pulling off the coefficients, making these scalar equations. What do I see is the equation 4 and equation 6. If I solved equation 4 for each other, TCD equals TBC. But right, equation 6 tells me exactly the same thing. This should have been, mixing it up here, BC and C. Right, I don't know where I'm getting a C from. They all terminate at D. Equation 4 and equation 6 are actually the same equation. So I did get 6 equations, but I only got 5 linearly independent equations. So if you're in Math 220 and matrices, you'll understand more what that means. But I only got 5 unique equations since 4 and 6 were actually exactly the same thing. So I have 5 linearly independent equations, and I have 5 unknowns. So my system is solvable in that way. Solving equation 4 or equation 6 gives me the same information. TCD does equal TBD, which just by inspection looking at symmetry, I knew that was true. But now mathematically, it's showing me the same thing. So they are equal to each other from equation 4 or through equation 6. And if I look at equation 5 now, since I know they're equal to each other, now I can use equation 5 to solve for both of them. Since they're equal to each other, putting that into equation 5, I get that both tensions are 117 newtons. This makes everything else much easier because in equation 1, 2, and 3, now that I know both of these values here, I can solve for the 3 remaining unknowns, the AX, AY, and AZ. So from equation 1, now I only don't know the value of AX. And that will be 66.7 newtons. I can solve AY from equation 2. And that does turn out to be 0. And finally, using equation 3, I can find the value that AZ is 100 newtons.